Welcome to today's lesson. We're going to look at what is a radian, and we're going to talk about sectors of circles and how that ties in with radians and trigonometry and a whole bunch of other things. So let's start off with defining a radian. Now, up to this point, you've known how to measure angles using degrees. There's another way to measure how big an angle is, and that's using something we call a radian. Now let me just show you where a radian comes from. It comes from a circle, and let's say we have a circle with a radius of length r. Well, what we do is we take that same length r and we measure it along the side of the circle, something we call the arc length of the circle. So we're going to measure off, and it would probably be something like to about there, so that this little point from here going along the circle is the same distance r. If we do that, the distance that we pan out here is referred to as 1 radian. So this angle, where the arc length is the same as the length of the radius of a circle, is what we call 1 radian. So, just how big is a radian in something that we know? What I'm going to do now is talk about the comparison between degrees and radians. I mean, I could look at that and I could kind of eyeball it. It looks like it might be something close to 60 degrees, maybe, something like that. But let's find out exactly what that is. And the way I'm going to start that, to make the comparison, is we're going to look at a circle, and we're going to say, well, in a circle, if we were to look at how many degrees there are all the way around to make a full circle, we would know there's 360 degrees in a full circle. So that, in a sense, if you took a bunch of little 1-degree sectors, we would have 360 of them. And that's something we're pretty familiar with. Now, to do the same thing with radians, I'm going to try and figure out, well, how many radians would there be in a circle? So the way I'm going to do that is I'm going to say to myself, why don't we take the full circumference of a circle, okay? So for the full circumference of a circle, I'll draw a second picture here. We know that the circumference we can mathematically calculate by going 2 pi times the radius. So that's how we get the circumference of the circle. So that would be the complete circle's arc length. And since we know that 1 radian has an arc length of r, all we have to do is take our full circumference and divide it up by how many sections have a length of r to see how many radians we get in a complete circle. So what we're basically going to do is say to ourselves, okay, how many of these r's are going to fit in the circle? And I'm sort of just drawing a crude drawing here, but this is what we're mathematically going to do. We're going to take 2 pi times r, which is the full complete circumference or arc length of the circle, and divide it up by r, which is the length of arc for 1 radian. We do this and we notice that the r's are going to cancel, and in a full circle there are 2 pi radians. That's how many radians there are in a full circle. So here's what we now have. If we take the two comparisons, we have 360 degrees on the one hand, and that's going to equal in radians 2 pi radians on the other hand. And I better write radians or it's going to look like r as in radius of the circle, but what I mean here is 2 pi in radian measure. That's how many radians we have. Now I can take this relationship and simplify it a little bit and get 180 degrees is equal to pi radians. Now here's a little bit about notation. If we mean degrees, we use the degree symbol. And if we mean radians, we either write the word radians or we don't write anything. Okay? So that's how you can tell. If you're talking about the angle measurement, then in radians it's very commonly left off. So now I have a very, very important relationship. 180 degrees is equal to pi radians. And what that means is, in kind of practice, is that if you took a straight angle being 180 degrees, that you would have pi radians. And that means just over 3 radians on a straight line. We're going to use this very, very important equation to help us convert from radians to degrees or degrees to radians. So let me show you how we can do that. I'll just work through a couple of examples here. In our first example, okay, we're going to start off and say, well, I wonder what 60 degrees is in radian measure. And the way we use our conversion here is we write on the degree side, which happens to be on the left side of my equation, 180 degrees, and we know that that equates to pi in radians. And now I can look at this and I can cope with it in 2 ways, and it's whichever way you prefer. We can either look at this and say 180 degrees, how did that become 60 degrees? Well, I could times it by 1/3. That changes the 180 to 60. So I got to do the same thing on the right side of my equation. So in other words, to compare 180 to pi and convert the 180 to 60, I divided by 3 or times by 1/3. And so my answer in radians is pi divided by 3. Now you could work this out and get a decimal number on the calculator, but it's very common with radian measure to leave it as an exact fraction. In fact, it's kind of preferred. There is another way that you can sort of think of the calculation here, which comes up with the same thing. Let me just write that out underneath here. Okay, start off with the 60 degrees again and say, oh, I want to get that in radians. Well, again, I write 180 degrees is equal to pi. And then I think of this as one fraction equal to another fraction. And to get the missing component, I just need to cross multiply and divide. So top times bottom divided by the remaining number. So if you think about what goes in here, by cross multiplying and dividing, you would have 60 times pi divided by 180. And in simplest form, of course, that's going to be pi over 3. Now, whether you prefer to think of modifying 180 equals pi and saying, well, which side am I going to modify to get this? Or if you like to cross multiply and divide, it doesn't make any difference. You get the same answer either way. Let me work through another example. Okay, this time let's see. Let's take 150 degrees and try to convert that to radians. Once again, I start with 180 degrees is equal to pi radians. This one is perhaps a little bit slipperier when you think, well, what am I doing to the 180 that gets me 150? So I'm going to use the cross multiply and divide technique. So the number that's going to go up here is going to be 150 times pi divided by 180. And of course, we like to put that into lowest terms. I recognize the top and bottom numbers as divisible by 30. So I'm going to do that and get 5 pi over 6 as my radian equivalent of 150 degrees. Now that's all really good. What about if we're trying to get from radians to degrees? Well, let's look at an example of that. Suppose we take something like pi over 4 And we want to know what that is in degrees. Again, I'm going to start off with what I know, which is pi is equal to 180. Now you'll notice I make sure that the radian side is straight below the radian side. Pi is below whatever radian angle I've got here, and degrees are in this case on the right side. Now, cross multiplying and dividing is a little bit messier here, although it does work. But I think it's in this case easier to just say, why don't I just multiply by 1/4? That's what becomes pi over 4. And I'll do the same thing on the right side. So I'm going to take 180 and divide by 4. Easy enough, 45 degrees. Let's look at another one. This time I'm going to take one that may not be quite so obvious. 2 radians is how many degrees? Well, the system is the same. We start with pi is equal to 180. And in this case, the cross multiplying and divide seems to be a pretty easy approach. So I'm going to get 2 times 180 and divide that by pi. So the number that has to go in here is 360 divided by pi. Now, that would be something, because we're talking about degrees here, would probably be best done in a decimal form on the calculator. So I would just go 360 degrees divided by pi, and whatever number that is the answer in degrees. I'm going to leave mine here as an exact number. Okay? So that's the world of conversions when you're talking radians and degrees. Next thing we're going to look at is another look back at the sector of the circle. Okay, so when we're talking sectors of circles, what are we talking about? Well, let's just draw a circle. The sector of a circle is kind of like the piece of pizza. This is what we call a sector. And there's various components that are very important when we talk about a sector. Usually we talk about the sector angle, which I'm going to call theta. We also talk about the arc length of the sector, which I'm going to designate L. Not a very good L. Let's try that again. There we go. And I'm going to put in R to represent the radius of the circle. Now there are 3 important ratios when we talk about sectors and circles. And all of them share one thing in common. We're always talking about something about the sector and we compare it to something on the circle. So keep that in mind. It's always sector to circle. Now the first set of ratios that we talk about are the angles. And the sector angle is theta. And the circle angle, which would be the complete circle, if you're working in degrees, it's 360 degrees. And if you're working in radians, then this ratio would be theta over 2 pi. So it depends whether you want to work in degrees or in radians. Now this ratio, and this is when we're talking angles, this ratio is equal to another ratio which refers to the arc length. Now, arc length of the sector, that would be L. And arc length of the circle, okay, let's see, the arc length of a complete circle, that's the circumference of the circle, which can be calculated with 2 times pi times the radius. And then there's one last set of ratios which talks about area. Now, area of the sector, well, there's no real fancy way to write that. Sector area. That's pretty fancy, I guess. Pretty direct. Sector area. It's the area of the sector. So we're kind of talking about this. Okay. What about the area of the complete circle? Well, you might remember that's pi times radius squared. So we have these three ratios, all of which are equal. And what they do is they allow us to solve for any one missing ingredient. And some of these are very difficult to solve using any other techniques. For example, how do you measure L? You know, what do you do? Put a little string here or something and try to measure L? I mean, it's pretty tricky to do. But with these ratios, it's not too bad. So let me do an example of this and show you how these ratios can help us. Okay. Okay, in this first example, we're going to try and find the arc length. We're going to try and find the arc length given some information. Given theta equals 2, and you'll notice that there's no degree symbol. What that means is that I know this angle is measured in radians, 2 radians. And another bit of information, and the radius equals 10. Okay. So we're going to try to find the arc length. Now, if you have trouble visualizing this, I really recommend drawing a picture and trying to fill in some of the blanks. Okay, let's just draw our picture. Now, 2 radians is kind of like, well, we know 3 radians, just over 3 radians is 180 degrees. So we could approximate 2 radians to be something around 120, just to get a kind of a decent picture. So let's draw it something like this. So there's our sector, 2 radians. We don't know L. In fact, that's what we're trying to find. And we know the radius is 10. So there's all of our given information. And what I'm going to do, since we're given this angle, I'm going to start off with run ratio that says the sector angle compared to the angle of the circle. Now, because this is in radians, I'm going to make that radians as well. So I'm not using 360 degrees, I'm using 2 pi. The next ratio will be arc length of the sector compared to arc length of the circle, which is 2 pi times the radius, and we know the radius is 10. Well, there it is, everything in place. All I have to do is cross multiply and divide, and that's going to solve for L. So L will equal 2 times 2 pi times 10 divided by 2 pi. And you see what very nicely happens is the 2 pi's cancel, and the answer is 2 times 10, or 20. It's really that simple. If you set up the correct ratios, it's quite easy. Okay, that's about all there is about sectors, at least for today. And I'm going to do a little bit more now and talk about angles in standard position. Now, a lot of this is terminology that might be familiar to you, and if not, it's a new learning experience. So, angles in standard position. When we talk about standard position, we're talking about the good old XY axis, and we kind of use the like hands of a clock, and we build angles with these 2 hands of the clock. The first arm is always on the positive x-axis, and this is called the initial arm. It's kind of like the first hand of the clock. If we swing the other hand in a counterclockwise direction, and that means going this way, we refer to those as positive angles. So let me just draw one. For example, I wanted to draw 60 degrees. That would swing up to about there, and this would be 60 degrees. Okay, and if you want, I can just show I've swung upwards. Okay, and that's the positive direction. So I can draw pretty much any angle that I want. 60 degrees. I could have kept going and drawn 180 degrees over to here. I could swing below that and draw something like 200 degrees would be a little bit lower than that, so something like that, and so on. I mean, the sky's the limit. A little bit of terminology as well. The arm that finishes the angle, the one that actually swings through a certain amount of angle, is referred to as the terminal arm. Okay. Now I talked about swinging in this direction as being the positive direction. What about swinging the other direction? Well, guess what? Those are the negative angles. So, for example, if I wanted to draw negative 40 degrees, it would be starting from here, 40 degrees in the clockwise direction, the same way that the hands of the clock move. So we can draw, again, any angle you want. The sky is the limit, whether they are negative angles or positive angles. Okay. Now another bit of terminology is we could draw the same location here, the same terminal arm, but it doesn't have to go through negative 40 degrees. I mean, what if I went in the positive direction and I ended up with the same terminal arm? Now if you think about it, a full rotation all the way around would be 360 degrees. And if I'm just 40 degrees shy of that, then that would be swinging through 320 degrees. They have the same terminal arm. And the term for that is these are coterminal angles. And you can start to think these aren't the only two coterminal angles. There's going to be an infinite number, because I could go 320 degrees, but who's to say I stop there? Why don't I throw another little rotation in? So I could go and say, well, I could have done 320 plus another 360. So what would I get? Looks like 680 degrees. I could certainly do that. I could take 680 and add another rotation. Why? The sky's the limit. Now, I'm not going to add that up. You get the idea. I could also have taken negative 40 and said, well, you know, why don't I swing another negative 360? So I'm going to tack on another negative 360. So another coterminal angle would be negative 400 degrees. Now I could keep going and list billions and basically use up all the time we have, but there's a nice little shorthand way of writing that. So let me just get some room here and show you the shorthand way. Instead of trying to list all the angles, you could do something like this. You could say, well, let's take negative 40 degrees and add multiples of 360. Now, n here, we usually put a little designation that it's an element of the set of integers. Okay, so what this means is that n is a number like 1, 2, 3, 4, or it could be 0, or it could be negative 1, negative 2, and so on. And if you do that, what you're doing is saying I'm going to either add 360 degrees to it, or I'm going to subtract 360 degrees and multiples of it. By the way, sometimes you see this written like this. N is an element of the set of integers, but you got this big funny looking Z. That does mean integers. It's actually from the German word Zahlen, which means numbers. So this is kind of a compact shorthand way of writing it. It's common, it's one little change I'm going to make here, it's common not to use the negative angle, but rather the smallest positive angle. And that smallest positive angle in this case is 320 degrees. So it's more common to write it like that. Okay, this is the preferred. And we use the smallest positive angle rather than the negative coterminal angle. There's one other very important angle that we need to talk about here. And that's an angle called the reference angle. Now, its incredible importance will not be apparent today, but in lessons in the future you'll see just how important the reference angle is. So let me just mention what a reference angle is. If, for example, we drew something like 200 degrees, okay, so that would mean from our starting arm, our initial arm, 200 degrees in the positive direction. So there we go, we're swinging through 180 and a little bit more, something like that. What would be the acute angle going from the terminal arm to the x-axis? Well, if you think about it, you've gone 180 degrees to get to here, and another 20 to get to 200. So there is a 20-degree angle between the x-axis and the terminal arm. And that little angle, very important angle, is called the reference angle. So just for your notes, we're talking about the angle between the x-axis and the terminal arm. And I'm even going to add here it's acute. It's always less than 90 degrees. So as one final example about reference angle, let's just find the reference angle for, let's go with negative 300 degrees. Okay, I would start with a picture. Now negative 300, so we're going to start here and swing through negative 180. And we're going to keep basically going. I like to think of it this way. We've gone a full rotation, which would be negative 360. And oops, that's too much. So I'm going to back it up by 60. So we're actually going to end up about here. Okay, so there's my negative 300. Had I gone to 360, I'd have gone all the way around. But the angle that's left between the terminal arm and the x-axis, that acute angle is 60 degrees. And that is our reference angle. Notice the reference angle is not considered to be negative. It's an acute positive angle. And with that, I think that's all we really need to look at for today. We'll catch you later.